So there are two parts to fundamental theorem calculus. One part we've already been using. So I think it's part, I don't remember actually which thing is named which. I believe the fundamental theorem calculus part 1. I should look in the book. Let me look in the book just so I can be so I can say it the same way. Most people say part 1 is the part we're going to talk about today. Let's take a look here. One moment, please. Sorry, I should have looked earlier. Section 5.4. Fundamental theorem calculus part 1. Yeah, that's the part we're going to talk about today. Part 2 is the part we've been already using. So part 1, I'll fill in a second. Let's remind you that part 2 is really just the part that allows us to use antiderivatives to evaluate definite intervals. So it's the part that says the integral from a to b of f of x dx, which we should read as the net area under the curve f of x between a and b, is equal to capital F of b minus capital F of a, or as I will often write, capital F of x evaluated between a and b, where, of course, capital F of x is an antiderivative. So that's what the second part of the fundamental theory calculus said. It said if you want to calculate this integral, this definite integral, then you antidifferentiate the function, and then you plug in the top end point, and you subtract, and you plug in the bottom end point. The other part of the fundamental theory calculus, the first part, is basically just talking about the relationship between derivatives and antiderivatives. And the very big picture thing to think here is that derivatives and antiderivatives undo each other. So if you take an antiderivative of a function and you take the derivative of that function, you get back to where you started. Here's how it's typically written. And I guess I should try and do, yeah, I mean, yes, there's nothing surprising here. Is the following, is that, so we need a few things. If f is continuous, and capital F of x is equal to the integral from a to x of f. Where, just so you're aware, x is the variable, right? This is a function of x, so x is the variable. A is a constant. Then the derivative here, f prime of x, is equal to the left of x. Sometimes you will write this as the derivative of the integral from a to x f of t dt. So basically, all this says is that the derivative of the antiderivative of a function is equal to the function. That's it. It can get a little bit more complicated depending on a couple things, but that is the big idea. Is that if you do the integral and you do the derivative of that integral, you end up with the function you started with that is the integrated inside. And this change of variables things happens, right? Usually we start off with some integral with t's in it, and we end up with some function of x's at the end. And I'll explain why that has to be true. But this is really it. So these are the two parts of the fundamental theorem calculus. I will also mention that I did post solutions to the quiz I gave. I haven't graded it yet, or really it's not so much that I'm going to grade it, so I'm going to give you feedback on it. So I'm going to like type things like, you did this, or you did that. The top part says, if f of x is continuous and capital F of x equals this integral of from a to x of f of t dt, I guess this is also supposed to be continuous. I don't really worry too much about that part. It's not something that's usually an issue for us. It's more that you have this, then the derivative is equal to the left. Oh, the red part, that says a VAR for variable. Yeah, so x is a variable and a is a constant. All right, so I did post the solutions, but it will ask me to go over the fundamental theorem problems anyway, so let's go ahead and go over those. Let me just remind myself what they are. But yeah, they are posted in the module section if you want to see them. So here is the first question. We have that g of x is equal to the integral from 1 to x of cosine of t dt. Right, here's the entire point of the fundamental theorem of calculus part 1. Is that you can do this quickly. You don't. I'm going to show the work, but we all already know that the end result is going to be that g prime of x is equal to cosine of x. The derivative of this integral of this function is just that function. It just happens to have a different variable. Instead of t, we're going to get x. That's it. That's all we're doing. So here's why this happens. I'm actually going to integrate this. So I'm going to find g of x as a function of x by doing the antiderivative of cosine of t. So what's the antiderivative of cosine of t? You guys are mostly right, except it's not sine of x, it's sine of t, because we're antidifferentiating with respect to t, and our variable is t. And then it's evaluated between 1 and t. Sorry, not 1 and t, 1 and x. So then we're going to plug in x first, and then 1. Okay, so now, if I'm going to find the derivative here, well, that's what's broken down here, right? So g prime of x is going to be the derivative of g of x, which is sine of x minus sine of 1. What's the derivative of sine of x? No surprise, cosine of x. What's the derivative of sine of 1? Exactly, it's 0, right? You know it's going to be 0 because there's no variables there. Right? I don't know what sine of 1 is. I think it's like, what is sine of 1? I don't know. Sine of 1, I think, is 1 radian is like 60. Sine of 1 is like 0.47, I think. But it's a constant, right? It's something that doesn't change. So the derivative of sine of 1 is just 0. If you don't see any variables there, even if there's a function, just like the derivative of e squared is also 0 because it's a constant, it's a constant. So we just get cosine of x. Again, this shouldn't be surprising. We antidifferentiated cosine, we got sine. We differentiated sine, we got back to cosine. So we got back to where we started. And the reason that we changed the variable is because we ended up doing this with t, but then plugging in x. So t is what we call a dummy variable. We need it to kind of play the role of the variable, but really x the actual variable we're interested in. In a similar way, we can do the same thing for the other question we asked, which was, grab it here, to find the derivative of the integral from 4 to x of, what do I got? 8t to the 7th plus secant squared of t. And now we can do this by doing very little work or a lot of work. The very fast way to do this is to say the derivative of the integral is just this function. We know the answer is going to be 8x to the 7th plus secant squared of x. I'm still going to show you the steps because it's good to see how this works a few times before we just start jumping straight to the shortcut. But the steps are, okay, antidifferentiate 8 to the 7th. You get 8t to the 8th divided by 8, which is just t to the 8th. And to differentiate secant squared of t, the function whose derivative is secant squared is, what's the function? What trig function is it? It's something I don't do very well. Tan or tangent is what I actually think. Tangent of t. Hopefully that means you laugh a little bit. And then from 4 to x. Oh, I forgot something. I forgot to write the derivative, right? I haven't taken the derivative yet. I've taken the integral. So I should still write the derivative of all of this. And then that's going to be the derivative of x to the 8th plus tangent of x minus 4 to the 8th plus tangent of 4. And then the derivative of x to the 8th is 8x to the 7th. The derivative of tangent of x is secant squared of x. And the derivative of 4 to the 8th plus tangent of 4 is 0, because those are both constants. So we again get exactly what we started with, right? Took this function, we anti-differentiated, we re-differentiated, and we got back to the function we started with. So that is really the whole fundamental theorem of calculus, part 1 in a nutshell. Is you do the derivative of the integral and you get the function that is inside the integral. There are a couple things we should address, but that is the main gist. And so the thing is, while these examples are functions that you can actually do the whole process for, right? You can anti-differentiate the function and then take the derivative of that. You can also use a fundamental theorem of calculus part 1 to do this for functions where you can't actually differentiate. The bottom line says the derivative of x to the 8th plus tangent of x minus 4 to the 8th plus tangent of 4 equals 8x to the 7th plus secant squared x. So we can use this for functions that are very hard or even impossible to anti-differentiate. Probably the most famous example of a function that's impossible to anti-differentiate is e to the negative t squared dt. This function, e to the negative t squared, is not anti-differentiable. Actually, the other way, Jason. We first do the antiderivative and then do the derivative, except we're not going to do that here. So the thing is, the whole point kind of the fundamental theorem of calculus is that you don't have to do any of the work. We know that if we differentiate the antiderivative, we're just going to get back the function that's inside the interval. The only difference is this function I'm calling f of t, this function I'm calling f of x. That's it. We're done. And it works, right, for anything. I want to do 5 to x, something really convoluted and messy looking, like t to the 3rd times sine of t squared over e to the t plus, I don't know, over e to the t plus 6. This is probably impossible to integrate. It looks very complicated. I don't care, right? We're not being asked to integrate it. We're being asked to take the derivative of the integral, which we know is just this function. So we're just going to say, okay, here's our answer. It's x cubed times sine of x squared over e to the x plus 6. That's all there is. It feels almost kind of dumb, right? Like it's just like, here's the thing, write the same thing with x's instead of t's. It does get a tiny bit harder. So let me actually, so what we're going to try and do in a minute, although we're not going to do it yet, is I'm going to ask you to do this. We're going to come back to this. So we're going to do the same one, where our function is t cubed sine of t squared over e to the t plus 6, except we're going to differentiate the integral from 5 to x to the 4. And we're going to see that that's actually going to make a difference. But let's do some examples we actually can antidifferentiate to see how that works. So let's see, what's another function we have that's pretty easy to differentiate? We'll do this. So let's say my function, let's say I want to differentiate the integral from 2 to x cubed of, I don't know, let's say we've got, that's not the best example I could pick. Sorry, I was going to pick something that, I feel like there's an extra layer of confusion there. So let's do something like, I don't know, 4t cubed plus sure. Sorry, we'll do sine. Okay, so here, this problem is going to be a little bit different. The answer is not just going to be 4x cubed plus sine of x. It's also not just going to be 4x cubed plus sine of x cubed. This is still the FTC part 1. Yeah. This is, and in fact, if you're looking at your textbook, do they talk about? They must talk about this in your textbook. They should talk about this in your textbook. They're really not talking about this in your textbook. That seems crazy. They give some examples of this part, but there's kind of a general rule for this. So I'm going to talk about the general rule. Yeah, interesting. I don't say that in there. It surprises me. Okay, so here's the idea. We're going to do it the long way. We're going to antidifferentiate first. So we're going to get still the derivative of the antiderivative here. So the antiderivative is going to be t to the 4th. Right, the derivative of t to the 4th is 4t cubed. And the antiderivative of sine of t is going to be minus cosine of t. Because the derivative of cosine is negative sine, so the derivative of negative cosine is positive sine. Between 2 and x cubed. So then I'm plugging my x cubed. I get the derivative of, and now I could simplify this, but I'm actually not going to simplify it. I'm going to write it as x cubed to the 4th, even though we could totally write it as x to the 12th. I actually couldn't simplify this and write this as cosine x cubed minus 2 to the 4th minus cosine of 2. We don't care about, 2. We don't care about this part. We know that the derivative of this part's going to be being 0, right? The part you plug in the constant is really not important at all. Okay. So yes, I know the derivative of x to the 12th is 12x to the 11th, but I'm going to do it using the chain rule. The derivative of x to the cube, x to the 3rd to the 4th. So I've got something to the 4th power. So the derivative of something to the 4th power is 4 times my something to the 3rd power times the derivative of that something. So it's going to be 4 times x cubed times the derivative of x cubed, which is 3x squared. And in a similar way, the derivative of minus cosine of x cubed, well, the derivative of negative cosine of some stuff is positive sine of that same stuff times the derivative of the stuff. This is going to be plus sine of that stuff times the derivative of that stuff. Minus 0. Now here's what I want to point out. From each of these, I can factor out a 3x squared. So here's what I get. I think I have nothing down here. So I get 4, I'm still going to write it as 4x cubed plus sine of x cubed all times the derivative of x cubed, which is 3x squared. Here's how you could relate this back to the original question. So in the previous problems, we could just take this function that we're integrating and differentiating and just plug in x. So like if this had been the derivative from 2 to x of 4t cubed plus sine of t, the answer would be 4x cubed plus sine of x. But now what I can do is I can, instead of plugging in x, I can plug in x cubed. So I'm plugging in x cubed for every t. But then I also have to multiply by the derivative of x cubed because of the chain rule. Right there. So if your upper limit of integration is more complicated function than just x, you're still going to plug it in for t, but you're also going to have to multiply by the derivative of that more complicated function. So let me show you another example before we get to the one I left on the other side of the board. And yes, you can simplify that. I don't want to simplify that. That's not really the point here. Yeah. So what if I wanted to find the derivative of, say, be careful here. Show the integral from take care of 3 to x squared of 1 over 1 plus t squared dt. Yeah, that was the final answer. I mean, again, you could simplify it. I don't want us to worry about simplifying these, but yeah, you can simplify this as like 4x to the 9 plus I of x cubed all plus x squared. But the real point here is if you're differentiating the integral like this, where the upper thing is the sum function of x, you plug that into the t's and you multiply by the derivative of that. So in this case, although I could antidifferentiate this, I know that I'm going to get the answer by plugging in x squared for my t's. So I'm going to get 1 over 1 plus x squared squared. But then I have to multiply by the derivative of x squared, which is 2x. And then, yes, you could totally simplify this one as 2x over 1 plus x to the 4th. That's it, though. I will also mention, you could do this one the long way. You could say, oh, well, this is equal to the derivative of, what's the antiderivative of 1 over 1 plus t squared? It's the arctangent of t, evaluated between 3 and x squared. So then I plug in the arctangent of x squared minus arctangent of 3. And then the derivative of arctangent of some stuff is 1 over 1 plus the stuff squared times the derivative of the stuff, right? It's really just literally the chain. And then minus the derivative of this is just minus a 0. And that's equal to that. So now to this example down here, right? This example that we cannot actually differentiate. Here's all we have to do. We plug in x to the 4th wherever we see a t. So it's going to be x to the 4th to the 3rd times sine of x to the 4th squared over e to the x to the 4th plus 6. And then what do I have to multiply by at the end? I need to do something with a chain rule. I remember how on this one I multiplied by 2x at the end. This one I'm going to have to multiply by 4x cubed. Right? The derivative of x to the 4th. Yes, I can totally talk about the arctangent one again. So the arctangent one, again, so the short way, the quick way, is we plugged in x squared, right? That is an x squared up there, just so in case you can't quite see it. I plugged in x squared wherever I saw a t. So I got 1 over 1 plus x squared squared. And then I also had to multiply by the derivative of x squared, which is 2x. And we exactly see that if we actually do it the long way, right? The integral of 1 over 1 plus t squared is arctangent of t. I plug in my upper endpoint and my lower endpoint. So I get the derivative of arctangent of x squared minus arctangent of 3. And then the derivative of arctangent of x is 1 over 1 plus x squared. The derivative of the arctangent of some stuff is 1 over 1 plus the stuff squared times the derivative of the stuff, right? That is the chain rule. So the derivative of arctangent of x squared is 1 over 1 plus the stuff squared, so x squared squared, times the derivative of the stuff. And the derivative of x squared is 2x, which is exactly what we have up here. I just didn't simplify it. In fact, there's something else I want to mention here. I know what it is. So here's what we have generally. I'm gonna write down both versions of this. And again, for those of you that might have come in just recently, we're talking about the fundamental theorem of calculus part 1. So the usual way of writing this is the derivative of the integral from a to x of f of t dt is equal to f of x. Again, where x is a variable and a is a constant. And then we also have this other version, which is really the chain rule version, which is that the derivative of the integral from a to some function of x, g of x, of f of t dt. Well, again, so here I plugged in x, I got f of x. Really, you could think of using the chain rule here. I plugged in x, I got f of x, and then I multiplied by the derivative of x, which is 1. I'm going to do the same thing here. I'm going to plug in g of x. So I'm going to get f of g of x times the derivative of g of x, which is g of x. That's how the more general or chain rule version of the fundamental theorem of calculus part 1 actually works. And really, it's just, it's really just the chain rule. What's happening here, right? If you remember, so I'm going to go back a little bit to the more definition, right? We said this. We said, actually, let me make sure. Yeah, we said, we said capital F of x is the integral from a to x of f t t. And then the derivative of f of x is equal to f prime of x, which is f of x. Right, because capital F is the antiderivative of little f, the derivative of capital F is little f. Well, we can do the same thing for the chain rule, right? I'm going to plug in a g of x for x. So I'm going to say capital F of g of x is the integral from a to g of x of f of t dt. And then if we take the derivative here, well, look, I know how to take the derivative of a thing like this. The derivative of capital F of g of x is f prime of g of x times g prime of x. But capital F prime, right, the derivative of the antiderivative is just f. So this is really just f of g of x times g prime of x. Or as I like to say, if you're differentiating an integral like this, you plug in the function of x everywhere you see t, and then you multiply by the derivative of that. Okay. One or two more things about this, and then we will. I think my plan is to move on and start talking about some new substitution, unless there are other things that people really want to see. Definitely go over this again. Yeah, this definitely takes a little bit of getting used to. So I'm going to go over this whole board again, just because I think it's worthwhile. So again, here's what we write. Here's the fundamental theorem of calculus part 1. Right, derivative of the integral of the function is just a function. And here is the chain rule version of it. The derivative of the integral from a to g of x of the function is f of g of x times g prime of x. And the reasons for that are because of how we define the antiderivative, right? The antiderivative, capital F of x, is equal to the integral from a to x of f of t dt. Right? That is an right? I should say there are multiple antiderivatives of a function. This is one of them, capital F of x. You can do another one that was different by a constant. The second step, I'm not sure where you mean. Like here? Okay, so let me go explain it this way and we'll come back to that. So this is the antiderivative, integral from a to x of t dt. And if capital F is the antiderivative of little f, then the derivative of capital F is equal to little f. Right, that's what's happening here. This is how the final theorem calculus is working. And then what I'm saying is, well, if f of x is defined to be the integral from a to x of f of t dt, we can also similarly define capital F of g of x by just replacing x with g of x. So then I've got the integral from a to g of x of f of t dt. And then I'm going to take the derivative of this. Well, I know how to find the derivative of f of g of x, right? The derivative of a composition of functions, you differentiate the outside thing, you leave the inside thing alone, and then you multiply by the derivative of the inside thing. But then, and it's really important, right? We know that capital F prime of whatever, right? Capital F prime of x is little f of x. So capital F prime of g of x is little f of g of x. And so here we see that the derivative of f of g of x, well, that's just the derivative, right? F of g, capital F of g of x is this. So the derivative of the integral from a to g of x of f of t dt is equal to little f of g of x and g prime of x. So you don't need to really know this super, I mean, you need to know like the ideas here, but like all this kind of very not specific example notation is not super important to be great at. What's more important is that you can do examples like this one, like what's the derivative of the integral from 2 to x cubed of cosine of t times sine of t dt. Cosine of t times sine of t is something we'll eventually learn how to antidifferentiate, but we probably don't really have the ability to yet. We might, I don't know, you might, you can do what you said, I guess. That's not the point. The point is never, if you see a derivative of an integral, you never actually want to antidifferentiate anything. All you want to do is jam this in there. And then what do I have to multiply by? Everybody. Everybody. Somebody. Yes, thank you. Exactly. The derivative of x cubed. That's how it works. There's two other variations of this. These are not nearly as hard. So what if instead I had the integral from, I don't know, say the natural log of x to 5 of something like, I don't know, t squared over 1 plus t dt. How is this natural log of x, or this function of x in general, being in the lower limit of integration, how is that going to change that overall answer? Well, one way we could deal with it is to just do the thing that we need to do that allows us to flip the order of the limits of integration. The question is, how do I do this, right? How do I deal with it if the variable is in the lower limit instead of the upper limit? And I'll talk about kind of the straight easy answer in a second. But yeah, exactly, Sophia. We're going to make it negative. I'm going to write this as the negative integral. Oh, you know what? I'm sorry. It might not have been super clear because I forgot the derivative symbol. I apologize. I meant to ask, what's the derivative of the integral from natural log of x to 5 of t squared whole plus t? And yes, you're exactly correct. It is equal to the negative of the derivative of the integral from 5 to natural log of x of t squared 1 plus t dt. And then we could just do the regular thing. We could say, okay, that's going to be negative. The derivative of the integral, I'm going to plug in the natural log of x. And with the natural log of x squared over 1 plus the natural log of x times the derivative of the natural log of x, which is 1 over x. And that's how we would do that one. More generally, if you ever have your variable thing in the lower limit, it's always just going to be the negative of what it would have been, because you can always do this. So we could totally so back, let me just grab one thing here. Where'd you go? Sorry, right, you could totally do, that was not so fun. Yeah, let's do this one. You could totally do these two problems. Find the derivative of the integral from x to 3 of 1 over the square root of 4 minus t squared t. And then I also want you to find the derivative of the integral from e to the x to 3 of the same thing. And I'm going to refill my water while you guys work on that for, I'll give you 2 minutes. It really should take not very long at all. But so maybe less than 2 minutes. I'll be right back. That was probably less than 2 minutes, but probably enough time to at least do the first one. The first one's going to be, since it's in the bottom, you know it's going to be negative. It's going to be negative 1 over the square root of 4 minus x squared. Done. That's it. For this one here, tiny bit more complicated. It's also going to be negative because our variable thing is in the lower limit of integration. I'm going to get 1 over the square root of 4 minus e to the x squared, which you could simplify as e to the 2x. And then what do I need to multiply by? Yeah, you've already got the answer. Yes, exactly. The derivative of e to the x, which is e to the x. And this is pretty much what there is to the fundamental theorem of calculus part 1. Take the derivative of the antiderivative and you get the function you started with. And I mean, it is called the fundamental theorem of calculus because it's really spelling out the relationship between how differentiation and antidifferentiation work. And the thing you should remember a lot, sounds kind of silly, you should make it embed in your soul the fact that antidifferentiation and differentiation are processes that undo each other. So if you differentiate and then antidifferentiate something, or you antidifferentiate and differentiate something, you're always going to end up at the same function you started with a minor exception. So let me just point out, it does depend on which order you do it in. Sometimes you get something slightly different. So if I start with a function, something easy, like, I don't know, 7 x to the 6. If I antidifferentiate this, I'm just going to do an indefinite interval. I don't want to so the indefinite interval of 7x to the 6 is x to the 7th. And then the derivative of the integral of 7x to the 6 is the derivative of x to the 7th, which is what we started with, 7x to the 6th. However, if you do things in the opposite order, you're not quite going to end up with 7x to the 6th at the end. So if I first differentiate 7x to the 6th, I'm going to get 42x to the 5th. If I then antidifferentiate that, so if I do the antiderivative of the derivative of 7x to the 6th with respect to x, I end up with the antiderivative of 42x to the 5th. And then the antiderivative of 42x to the 5th is 42x to the 6th divided by 6 plus a constant, just 7x to the 6th plus a constant. So if you differentiate first and then antidifferentiate afterwards, your answer might be different than your original function by a constant. But other than that, differentiation and antidifferentiation, named for a reason, are processes that undo each other. So if you do one and then do the other, you essentially get back to where you started at. So I want to talk about use substitution, but before I move on to that, is there anything else? Are there questions you guys have about this, or is there anything else you would like me to say about fundamental integrative calculus? Sure. So yes, to Sophia's question, is it always a definite integral? Yes, when you're doing these problems where it's like where you're doing the derivative of the integral of something with a t in it like this, yes, it's always going to be definite because you have to have limits of integration where one of them is your variable. I would also point out, just because I could see someone trying to trick someone somewhere, I could definitely see, oh, there was one other type of question I meant to do. We'll do that, and then we will also, but also answer the other question. So I could totally see someone asking, hey, what's the derivative of the integral from, I don't know, 4 to e to the 5th of cosine of t squared plus t cubed dt. And everybody should be able to tell me that the answer here, it should only take you only have to type one character. What's the answer to this question? Using one character on your keyboard. Zero. There's no x's here. There's no x's here. If I'm differentiating with respect to x, right? So here's what I want to point out. If I did this integral is not a function of x, right? If I was able to integrate this, I would actually get a number, right? This is just some number, some constant number, because it's an area under a curve, right? If it's a definite integral with actual real numbers as the limits of integration, then you just get some area under a curve, which doesn't change, and then the derivative of that's going to be 0. If both of them are constants, yeah. On the other hand, and this is the one I forgot to do, if you differentiate something where both the top and the bottom are variables. So if you had something like, I don't know, the integral from x cubed to sine of x of t to the 4th over t squared plus 1 dt. In this case, you would essentially do it like you would do a normal integral. It's going to be top minus bottom. So first we'll deal with the top limit. We'll plug in sine. So I'm going to get sine to the fourth of x over sine squared of x plus 1. And I have to multiply by the derivative of sine, which is cosine of x, minus, then I have to do it for the bottom one as well. I'm going to get x cubed to the fourth over x cubed squared plus 1 times the derivative of x cubed, which is 3x squared. So when you have variables in your lower and your upper limit, you basically just do the rule twice. You do it for the top one, and then you subtract, you do it for the bottom one. And if you prefer, like if you want to know why, you can totally think of writing this integral as the integral from, say, like 0 to sine of x of t to the fourth over t squared plus 1 dt, plus the integral from x cubed to 0 of t to the fourth over t squared plus 1 dt. So that the derivative of this part would be normal, right? Plug in sine, multiply by the derivative of sine. And the derivative of this part would be normal, except it would be minus, because the variable's in the lower limit. Okay, and then back to the other question. So the reason there would be a constant up here is that when you do an indefinite integral, right? When I say what's the indefinite integral of 42x to the fifth, the question I'm really asking is, what is the function, or what are the functions whose derivative is equal to 42x to the fifth? And the problem with that question is there are multiple answers, right? So here I'm asking for an indefinite interval. So my answer could be 7x to the 6 plus 1, or it could be 7x to the 6 plus pi, or it could be 7x to the 6 minus 1,000. And each of these functions has a derivative that's equal to 42x to the fifth. And that's why if you were to differentiate a function first and then antidifferentiate afterwards, you don't get back to exactly where you started. That said, I'm still going to say generally that if you the antidifferentiation and differentiation are things that undo each other. So if you do them both, you essentially end up where you started at. You guys are asking good questions. Are there any other questions you have? Let me see. Let me grab the examples here. No, that's not what I want. Sure. Yeah, I mean, so again, the point of this, right? The whole point of this derivative of the antiderivative is that you don't actually have to do the antidifferentiation. The whole point is that we're just like, oh, this works the same every time. So we just plug in the limit of integration for all the t's, and then if it's more complicated than just x, we multiply by the derivative of it. So yes, it is definitely simpler. Where did the thing I wanted to go? Sorry, one second. Oh yeah, it doesn't look that too. Okay. So let's talk about U substitution. Which I often think of as kind of a way of undoing the chain rule. So let's start with an easy example. Let's do the integral of, let's see, I know it feels too easy. Let's make it a little bit harder than that. Let's do the integral of 2x times x squared plus 5 quantity squared dx. And this one, we definitely could multiply out, so we will. So this is going to equal the integral of 2x times x to the fourth plus 10x squared plus 25. And then we can multiply the 2x through and get the integral of 2x to the fifth plus 20x cubed plus 50x. And then we'll antidifferentiate. We get 2x to the 6th over 6 plus 20x to the 4th over 4 plus 50x squared over 2 plus c, which we can simplify a tiny bit. I get x to the 6th over 3 plus 5x to the 4th plus 25x squared plus c. Okay. Now I want to talk about doing it a different way. So here's what I'm going to say. I'm going to say that I'm going to make a u substitution. I'm going to pick u equal to some piece of this integrand. And there are a couple ways we think about picking u. And most of the time, both of those things are true. So I'm trying to pick u so that one, its derivative is also in my integrand. And two, it's kind of stuck inside another function. In this case, u equal to x squared plus 5 is the perfect candidate. Because one, x squared plus 5 is stuck inside another function, right? It's being squared. And two, more importantly, really, its derivative, which is 2x, is also showing up. So here's what we're going to do. We're essentially going to I think of this as like a translation problem. We are translating this integral that's in the language of x to the language of u. I'm not sure why you wrote x squared plus 5. Oh, you were answering my question, probably like what should I pick for you? Yeah. So I want to find the derivative here. Du dx is equal to 2x. And then I'm going to rewrite this as du equal to 2x dx. Because if I look at my integral, I have a 2x dx. People like to do this different ways. I personally like to make du look like something that is in the integral. But there are definitely people that like to solve this for dx and say that dx is du over 2x and plug that in for dx and then cancel the 2x's. That is not my preferred way of doing it, but sometimes it works better. So I'm going to write my integral, which is x squared plus 5 quantity squared times 2x times dx. I reorder the multiplication just to make it easier to see the pieces nicely together. This is exactly du. And this inside the thing being squared is exactly u. So I can rewrite my integral as the integral of u squared du. And all this means, right, since my variable and my differential match, right, this means I want to antidifferentiate u squared with respect to u. Just like if I antidifferentiated x squared with respect to x, I would get x cubed over 3. If I antidifferentiate u squared with respect to u, I'm going to get u cubed over 3 plus c. But we're not done. We're not done because the question started off asking us to integrate x squared plus 5 times 2x, or to find the antiderivative, right, the function. My answer can't be in terms of u because is the derivative of this equal to that? I don't know. I need to actually plug back in what u is. So it always sounds funny. I feel like I'm speaking incorrectly to say what u is, but you know what I mean. So I'm going to plug in u. I'm going to get x squared plus 5 cubed over 3 plus c. Now the question I want to ask, or answer, I suppose, is are these the same? Well, I don't know. I need to check. So let's multiply it out. Let's see. A little bit of room. I'm going to pick up the eraser as well. I'm going to go over here. So multiply this out. I've got 1/3 times x squared plus 5 cubed plus c. There is a pattern for multiplying out something cubed. it's going to be the first term cubed plus 3 times the first term squared times the second term to the first, plus 3 times the first term to the first times the second term squared, plus the second term cubed, plus c. Simplifying this a little bit, I get 1/3 times x squared cubed is x to the 6. 3 times 5 is 15 times x to the 4th. That seems wrong. I'm definitely worried now. Super worried. What the heck? Oh, I forgot about the one. I forgot about the one. I was like, oh no, this is gonna be wrong. So I was like 15 here isn't matching the 5 there. Forgot about the 1/3 up front. We're good to go. Okay. And then 3 times 5 squared is 75 x squared plus 125 plus c. And then distributing the 1/3, we get 1/3 x to the 6th plus 5x to the 4th plus 25x squared plus 125 thirds plus c. All right, so let me ask you guys, are these answers the same? You can give me a thumbs up for yes, a thumbs down for no. You can say yes or no. You can write yes or no. Do they look the same or do they look different? Okay, so they actually aren't exactly the same, right? That part's the same, that part's the same, that part's the same. But that part's a little different. Is it okay? Yes, it's okay. It is perfectly okay for antiderivatives. Right, exactly, Kimberly. It's perfectly okay for antiderivatives to be different by a constant. And that is actually something that happens on occasion. If you antidifferentiate something using a different method than someone else, your answers might actually literally differ by a constant. So be aware. If you simplify something versus you doing u sub versus maybe doing some polynomial division is a possibility. Oh yeah, we'll definitely go over another example. Depending on the method you use, you might get slightly different answers by a constant. Okay. So I also want to point out, just because I feel like I haven't said it enough, when you do an indefinite integral like this, your answer is a function, right? The function. When you do a definite integral, your answer is a number because it's representing the area. So I just want to make sure everyone's cool with indefinite, you get a function, definite, you get a number. Yes, we can definitely do more examples. So I should point out, this is going to be, so I'm just going to say something, the last 5 problems of the web work, I have looked at it a little bit, not a ton. Ooh, fun, yeah, those look real good. Gnarly, okay. Ugh, that's gross. Okay. So I'm gonna do, yeah, let me throw one at you that is similar to the problem 42, but not exactly. Let's say I want to find the integral of 3 inverse sine of 6x. That's gross. I don't like that problem. So the second over some dumb stuff. The square root of 1 plus 36x squared. This problem is real stupid. It's not that it's really stupid, it's just that it's, in my opinion, it's somewhat unnecessarily complicated. Fine. So here is the, again, when you're thinking u substitution, and that's all we're really thinking so far as methods, really you're trying to think about, okay, is there something in here? And I feel like, so you can definitely, you can kind of get tricked by this one. but we're looking for something whose derivative is also showing up. We're also looking for something that is trapped inside another function. You can make an argument in a couple ways, but there's only really one right answer. You could maybe argue something like maybe u is x squared, or even 1 plus 36x squared, because the derivative of x squared is 2x. The derivative of 1 plus 30x squared is 72x. And I have a something times x. Usually it's okay if we're off by a constant multiple. That's not the right choice to me. The right choice here is to let u equal 3 inverse sine of 6x. Because the derivative of 3 inverse sine is 3 times. What's the derivative of inverse sine? No, you can definitely do a u sub if it's definite. It's just more complicated. So if it's definite, well, we'll talk about that probably next class. If it's definite, you either have to change the limits of integration and then use them, or you can do the whole thing and then you go back to x's and then you plug in your limits of integration. So it's kind of like an extra last step or two. So do you guys know what the derivative of the inverse sine of 6x is? So the derivative of inverse sine of x is 1 over the square root of 1 minus x squared. So the derivative of the inverse sine of something is 1 over the square root of 1 minus that something squared times the derivative of this something, which is just 6. So here, my du dx is 3 times 6 is 18 over the square root of 1 plus 36 squared. And I've almost got that exactly. That 18 is kind of a pain. Yeah, you're definitely, you're right there. Yeah. So what I'm going to do is I'm going to rewrite this as 1 over 18 times du is equal to dx over 1 plus the square root of 36. Sorry, the square root of 1 plus 36x squared. But again, the thing I want to mention here, and just like problem 42 on your web work as well, is that you're looking to choose u so that the derivative is also showing up. So if you see something whose derivative is also there, that is your choice for u often. So then I'm going to replace this with what that's right. These are the same. So I'm going to replace this with what it's equal to. So I'm going to have a 1 over 18 du. And here's a good tip. Whenever you're doing u substitution, you always want to make sure you take care of changing dx to du first. You have to make sure all the x's, but especially that x, becomes a u. You can't have x's and u's. You have to have just x's or just u's. And this is the one that always gets forgotten. So make sure that dx does get changed to du. And then this part here, that's just u squared. Well, the rest is easy now. We know how to integrate u squared. It's going to be u cubed over 3 times 1 over 18, which we could simplify as plus c, which you could then simplify as u cubed over 54 plus c. And then finally, we'll plug back in that u is equal to 3 inverse sine of 6x. So we end up getting 3 inverse sine of 6x cubed over 54 plus c. Kind of gross. So I want to reiterate and re-stress that when you're trying to do a use, or if you think you're trying to do substitution, and this is going to be more of an issue as we learn more methods of integration, it's not always going to be immediately clear which method is the best method to use or the right method to use. And it's going to take some trial and error sometimes. But if you think u substitution is the method of choice, you're looking to choose u so that the derivative of u is also present in your integrand. Let's look at another example. I know someone had written an example. Let's see. So for the person who wrote me their question, I'm not exactly sure. I think it looks like this, but I'm not sure. I see this question, the integral of 6 over e to the 3x minus 2 to the 1/2 power. Did I get that right, or am I messing it up somehow? I kind of hope I'm messing it up because it looks kind of hard. I'm not gonna lie. Okay. All right. Huh. Yeah, that's a good question. So yeah. Oh, wait. So it's either. Oh. That's slightly less durable. So it's like this. It's like e to the 3x over 2. Oh no, I have it right. Okay, I'm not sure if I have it right. Is that correct?
So it was what you originally had with the square root of e to the 3x minus 2.
Okay, so it looks like this. Like that?
Yeah, and then someone said to solve it by using the u substitution and u equals 3x divided by 2.
Sure.
Or e to the 3x divided by 2.
Yeah. Huh. I feel like, yeah, let me think for a minute. Yeah, that's tricky. Okay, I'm gonna give you guys a slightly less terrible problem, but this one. So sometimes the problem is a lot of these problems require practice. And a lot of them require having done it a few times to know what the trick is. Oh yeah, this one is okay. So I'm gonna make it a little bit easier to see what the method should be here. So let's, instead of doing this, let's do the integral of 1 over minus 2, really? Minus 2. Okay. Whoever wrote this problem is, yeah, arc seeking is where we're going, is exactly it. But okay. So I'm gonna do a slightly different problem, and we'll see what the intention is here. I can even make it 9, sure. So if I let u here equal e to the x, my du dx is also e to the x, right? The derivative of x is e to the x. And the problem is, sorry, the dx here. I don't have an e to the x to kind of play, right, to suck up with the du. Right? I would normally say du equals e to the x dx, and then look for an e to the x dx to like replace du with. I don't have that. So then I have to kind of do something else, which is, so at this point, I would either say that dx equals du over e to the x. That's certainly an option, especially since e to the x is u. You can also do the other thing where you actually write this as natural log of u equals x, and then differentiate and say dx du equals 1 over u, like that. That's another way to go. That's called a power substitution. But basically, we're still doing u sub. So I'm going to rewrite this as, so my dx becomes du over u, and my square root there becomes the square root of e to the 2x is e to the x squared, which is u squared. And yes, now it looks a lot like an arc seeking thing. I always have trouble when it's 9 there, but I'm pretty sure, fairly sure, it's supposed to be the arc secant of the absolute value of u over 3. And there may or may not be a 1/3 out in front here. I'm not sure because this is the one that like I don't practice very often. So the way I would check is by taking the derivative of this and seeing if I get that. So the derivative of arc secant of some stuff, taking the derivative here just to check. Derivative of arc secant of stuff is 1 over your stuff times the square root of your stuff squared minus 1 times the derivative of your stuff. And I feel like I'm off by a little bit, right? Because if I cancel the 3 here and this 3 here, which they do cancel, I'm getting 1 over u times the square root of 1/9 times u squared minus 9. But that 1/9 I actually don't want. Square root of 1/9 is 1/3, so I need another 3 in the denominator to cancel out that 1/3 in the denominator. So there should be a 1/3 from here. And then you would plug back in u, and so you would get, sorry, I'm all over the place here, 1/3 arc secant of not u over 3, but e to the x over 3. And I drop the absolute values because e to the x is always positive. That is a tricky problem for sure. So for the version that was written to me in the chat, which was the integral of 1 over the square root of e to the 3x minus 2 dx, it's going to work out similarly. It's really garbage, though. Yeah, it's a terrible problem. But yeah, so you do the same sort of thing. So you would do, you would let u equal e to the 3x over 2 because u squared is e to the 3x. And then so yeah. So my du dx is e to the 3x over 2 times the derivative of 3x over 2, which is 3/2. So we end up getting, that's my u, right? Du equals u times 3/2 times dx. So dx equals du over u times 2/3. So that's gross. So that's what's going to go in here. So you're going to end up getting the integral of 2/3 du over u. You put the du over here. Okay, so let me ask you guys. This integral is going to be arc secant. It's going to be arc secant of u. It's going to be 1 over square root of 2 arc secant of u over square root of 2 times 2/3. That's pretty gross. And then you have to plug back in the u's. Some of these problems in web work I think are a little extra nasty, not on purpose, just because the program's like, yeah, I can throw in any constant here and it's just fine. So the problem is some constants are nicer than others, and you get very unnice ones like 2 there. An issue. The last thing I want to mention, I know I've only got a couple minutes left, but I'll address this more next time, is there's also this idea that I like to talk about, and Grant likes to talk about, which are called mini u substitutions, meaning things that you could use a u sub for, but you really should just be able to integrate without doing any kind of hard work. The examples I think of are like the integral of e to the 8x, or the integral of sine of 4x or the integral of 1 over 2x plus 3. Okay, I know the integral of e to the x is e to the x. I know the integral of e to the 8x is e to the 8x times some constant. Here's what I think about. If I differentiated, not integrated, right? If I differentiate, take the derivative of e to the 8x. The derivative of e to the x is e to the 8x times what? You guys are like, I'm not going to answer your question. I'm just going to be quiet. Not quite e to the x. So if I was going to do the derivative of e to the 8x, it would be e to the 8x times the derivative of the stuff, which would exactly be 8. So here's the thing. The antiderivative of this should equal this. The derivative of this should equal this, but it's off by a multiple of 8. So since the derivative makes me multiply by 8, the antiderivative is going to make me divide by 8. And that's true for all of these problems. The derivative of these things, where you have a multiple of x, would make you multiply by that constant. So if I was going to differentiate sine of 4x, I would get cosine of 4x times 4. Since I'm anti-differentiating, I'm going to get negative cosine of 4x. And the problem is that if I differentiate this, I would multiply by 4, but I don't have a multiple of 4 out in front there. So I have to divide by 4 to account for the 4 I would multiply by when I differentiated this and used the chain rule. Same deal here. I know the integral of 1 over x is the natural log of the absolute value of x. So I know the integral of 1 over 2x plus 3 is the natural log of the absolute value of 2x plus 3. But not quite, because the derivative of this is 1 over 2x plus 3 times 2. I don't have a times 2 here, so I'm going to divide by 2 to account for that. So in general, if you're integrating a function that you know, but it's like a function where you have something times x instead of just x, you typically end up dividing by that constant. One more example, just to kind of grab it home. I was going to integrate secant squared of 5x dx. I know the integral of secant squared of x is tangent of x. So the integral of secant squared of 5x is tangent of 5x divided by 5. Because the derivative here is secant squared of 5x times 5, and the 5 multiplies out to 1/5 to cancel. The 1/5, sorry, it's 1/5. So I'll talk a little bit more about many u subs next time, just because you don't want to have to like do a u substitution here, right? It's time consuming to say, okay, u equals 5x, and u dx equals 5, and do the whole thing, and change this to, 1/5 the integral of secant squared of u. And then integrate this and get 1/5 tangent of u, which is 1/5 tangent of 5x. So, all right, I've said enough.